Here we look at a simple animation of a spring mass system. Right now, this is in equilibrium here. The spring force is balancing out gravity. Now if I pull this down and release it, it's going to bounce up and down. I've set the friction equal to 0, so it should bounce up and down forever. The amplitude of the oscillatory motion is how far one way or the other it moves from equilibrium. And it looks like this might be about 5 centimeters or so. 5 centimeters above the mark and 5 centimeters below. The frequency is the number of cycles per second. The unit cycles per second has another name called hertz, but 1 cycle per second is 1 hertz. And the period is the time it takes to go up and down 1 full time. The easiest way to measure the period would be to measure the time it takes to go up and down 10 times. Let's see if I can do this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I get 6.26 seconds for the period. And so I would divide that by 10 and about 0.62 seconds. Let me grab this again. Let me see if I can grab it and stretch it out even more. Okay, so I've increased the amplitude quite a bit. And let me measure the period again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 6.25 seconds. So the period didn't seem to change with the amplitude, and that's pretty standard with all simple harmonic motion. The frequency or the period is 1 divided by the frequency, or the frequency is 1 divided by the period. The period gives you the seconds per cycle, and the frequency gives you the cycles per second. So you just have to, in this case, the period would be 0.625 seconds, and the frequency would be about 1.6 cycles per second, or 1.6 hertz. Another thing I should show here is, let me stop this thing by adding friction. Okay, and then I'll take this off, and then I'm going to put in a heavier weight. Okay, and then take the friction off and let this go again. I think without even timing this, you can see that the more massive weight bobs up and down slower. The period is longer, and the frequency is a lower frequency. Okay, this is fairly characteristic of simple harmonic motion, in that the more inertia the system has, the slower it oscillates. Okay, another characteristic of all simple harmonic motion is the idea that if you go to a stiffer spring, notice that the stiffness of spring 3 is much greater than that of 1 and 2, but a stiffer spring will give you faster oscillations. Okay, and pretty much any oscillating system behaves this way. The bigger the inertia, the slower the motion, and the stiffer the restoring force, the slower the motion. Okay, let's quickly go over to a pendulum. This is another oscillating system, and we'll explore this in lab. But the inertia of this system is a little bit more complicated because this is a mass that's rotating. The inertia of this system is actually related to how far the mass is from the center of the rotation. But one thing that we can look at is if we go to the moon, the oscillatory motion is much slower. If we go to Jupiter, it swings back much faster than if we're at the Earth. Okay, let me just reset this here. Again, so here's the Earth. And now let's go to the moon. much slower on the moon because gravity isn't very stiff. It doesn't restore things back to the equilibrium position very fast. And then let's go to Jupiter. Gravity is much stronger on Jupiter, about 2.5 times that of on the Earth, and so it oscillates back and forth much faster. Okay, good.